The second topic is Bluepilling. It's the project that we implement on the base Bluepill source code. I will talk about it later. Then Bluepill is the code that allows Bluepilling the Xen Hypervisor on the fly, and some words about Bluepill detection and how to detect Bluepill inside Xen. So that's a virtualization. Here we have a picture about a typical scenario that will happen if one of the nested virtual machines tries to enable nested virtualization. So in that bar, you see a typical hypervisor, which is primary hypervisor like Xen, for example. It runs multiple virtual machines, and one of them tries to become a hypervisor. So if we allow that, we should somehow implement a support for its guests. Like these nested hypervisors should think that it's the own hypervisor present in the system, because original hardware virtualization extensions are do not support this type of features. So this VM2 is a nested hypervisor. Consider it runs two virtual machines, like VM21 and VM22. And if the nested virtualization is implemented correctly, then we should allow unlimited depth of this nesting. So VM22 can become a nested hypervisor itself. So it will have two more guests, for example. So let's think how to handle this situation. So this is the picture of the relations between these virtual machines. So this is the arrows illustrate how should we route events from one hypervisor to another. Like VM221, for example, the lowest virtual machine in the picture, should be serviced by a hypervisor which runs in VM22, and so on. So the idea is to implement a flat scenario for one major hypervisor, which we call primary hypervisor. And from the point of view of this hypervisor, all these virtual machines are the same. So they all have the same privileges. So the details are very interesting because I said it before, CPUs do not support nested virtualization by default. So we have to implement some scheme that allows to correctly handle this. And let's start from AMD systems. So AMD SVM, the CPU extensions, implemented using a few instructions, like a few additional instructions. The main instruction is called VMrun, and it takes a pointer to VM control block as its argument. And this control block stores the state of the client which should be virtualized. So when VMrun instruction, when CPU encounters VMrun instruction, it stops the execution of the hypervisor and begins the execution of the guest until it meets some VM exit. Let's say we have to intercept RDMSR instruction. So if we set that we want to intercept this instruction in the VMCB structure, then it will generate, the CPU will generate VM exit, and it will return execution to the VMCB of VMCB 0 to the hypervisor, and then hypervisor takes some measures to service this instruction, and when runs this VMrun instruction again, and the guest continues. But what happens if the guest attempts to run a VMrun instruction? So basically, what happens with when the hypervisor has a guest that wants to be a hypervisor too? And this new VMrun instruction that the guest runs has its own argument, and it points to some another VM control block.
We will call it VMCB1. And of course, it will generate a CPU VMExit2 because VMRun is an obligatory intercept for AMD. And the main hypervisor will pop up, and then it should do something to run a service handler for this VMRun instruction. So the idea is to update this VMCB1 control block 1 with a few updates for handling another interceptions. Like VMCB structure holds a set of events that should generate VMExit, but we are not sure that all the VMExits that we want to intercept are set there. So we update this VMCB with another interceptions that we want to intercept as a main hypervisor, and we continue, and we should somehow continue the execution of the guest. And what should we do if this nested guest attempts to run RDMSR instruction? So let's see what happens if this RDMSR instruction has to be intercepted by the nested hypervisor and, of course, by us. So how should we route this information about the interception? According to our scheme on the one of the first slides, all the VM control blocks share the same privilege level. So they all will, all the VM exits that happen in these control blocks will generate VM exits to the main hypervisor. And the main hypervisor will see that this RDMSR was generated by VMCB1 prim. So this VMCB, we created this VMCB especially for handling this nested scenario. It was not created by original main hypervisor, but it was created by a guest hypervisor, and we updated it. So we have to somehow inform the nested hypervisor that an event has happened in its guest. And to do that, we have to continue the execution of the nested hypervisor, the VMCB1, VMCB0, with the information about this event happening in its guest. And to do that, we emulate the CPU behavior, which is supposed to continue the execution of the nested hypervisor, of the hypervisor, right after the VMRun instruction. And the RAX register should be filled with the valid physical address pointer to the VMCB1. And we also fill VMCB1 with the event that was returned to us in VMCB1 prim. And this is why the nested hypervisor will think that it receives the event from its guest, because it analyzes the value in RAX register. There are some problems, though. It's not that trivial to implement this scheme. So in these white arrows show the places where general interrupt flag, a global interrupt flag, should be modified by the CPU. So this feature was new to the AMD architecture. It was released with hardware virtualization extensions, and this global interrupt flag should be set to 1 by the CPU on the first instruction that a guest is going to execute right after the VMRun instruction executed by the hypervisor, and it should be turned to 0 automatically on each VM exit. So when we see global interrupt flag set to 1 here, that would mean that the guest is going to to receive all the interrupts that happen in the system, in its virtual environment, of course. But on each VM exit, the CPU automatically clears it to 0. So we have to somehow emulate this scenario, because if we do not set global interrupt flag to 0 on every VM exit, then the nested hypervisor will receive some interrupts. It can receive some interrupts, but it might be not prepared to receive these interrupts. And this is why crash will happen. So how should we implement this behavior of the general global interrupt flag? This is the illustration of this behavior. So we have to modify the value of this global interrupt flag, but we cannot intercept its modifications. There are two instructions to do that, to modify the value of this flag. Set STGI and CLGI. So setting global interrupt flag and clear global interrupt flag. But we cannot, there is no field in VM control block to set or clear this flag, because it is global for all the virtual machines. So we have to modify the behavior of the interrupt, how interrupt come into the guest somehow. So we use, so we need to emulate this general global interrupt flag, and we use these valid interceptions for STGI and CLGI instructions. But our handlers for these instructions have to support the modification of the interrupt masking field inside VM control blocks. So in every CLGI and STGI handler, we modify these values in the VM interrupt masking. So we actually mask the interrupts in the guest, and we also handle DBs, and we modify these fields in the VM control block when the guest, when the nested hypervisor should receive the information about global interrupt flag, that it should be set to 1. So all the interrupts should be enabled. VM load and VM save also have to be intercepted, because they address the nested VM control blocks. We have to modify them correctly so that guest will get the valid information, the guest hypervisor will get the real information from them later. Also, it's a good idea to virtualize host save area physical address, because it should not be modified by nested hypervisor. So it should be modified by the nested hypervisor, but we cannot change this value on the real machine, because there is no stack for these physical addresses. So we have to store each of them and then substitute this value in the intercept handler for the host save area machine-specific register. What about ASID conflicts? Consider this scenario when the primary hypervisor has ASID 0 and it launches a guest, and assigns it ASID number 1. So ASID is a new feature from AMD which enables tagged TLB caches, so that VM exit should not will not generate a TLB flash on every world switch. But there is a limited number of these ASIDs. Currently, AMD supports 64 ASIDs from 0 to 63. And ASID 0 is reserved for the use of main hypervisor. So if we run a nested hypervisor in ASID 1, this hypervisor still thinks that it runs in ASID 0. And later, it can launch its own guest and assign ACID1 to this guest. So we have to handle this situation, and we should update VMCB1 prim accordingly. So we have to control what ACIDs have been assigned and what are free. So if we support this tagged TLB feature, we have to implement these algorithms for modifying ACIDs as well. A few words about performance impact. As you saw in a general picture about the nested virtualization for AMD, it introduces only one VM exit on every original VM exit that should happen in the system. Also, we have to intercept STGI, CLGI, vmload, and vmsave instructions, in addition to vmrun, for example, which is obligatory intercept. We also have to intercept everything that nested hypervisor intercepts, of course. We have lots of optimizations space here. So I will show the picture about performance impact later when I discuss paravirtualized domains on AMD. What about Intel? There is no global interrupt flag on Intel, so it's a bit simpler to implement nested virtualization on Intel. There is no tagged TLB support right now, no ACID conflicts too. But VMX instructions take different type of arguments. They can be, the arguments can be addressed through a complex addressing scheme. So we have to implement some kind of instruction parser to see where these operands actually reside in memory. It's not that complex code though. We implemented this nested virtualization for Intel, but we cannot share the source code for it because it's copyrighted. The nested virtualization actually has been implemented many years ago by the IBM System Z mainframes. It's very cool. But the manual says that it's not a good idea to use this nested virtualization feature in a production environment because it is intended to be used only for testing purposes. And also, a few weeks ago, we received an information that KVM project implemented nested virtualization for AMD systems. So I think it's not included in the mainline code, but it exists as a patch for the main KVM code. So if anybody interested, you can see how this nested virtualization is implemented in a real-world hypervisor. Bluepill boot. This is a project for illustrating the possibilities of using the virtualized malware in a more complex way that it was used before when a new Bluepill was implemented. Bluepill boot is based on a Bluepill source code, or new Bluepill source code, but it does not require any particular operating system to execute. So it installs in the master boot record or maybe BIOS, it doesn't really matter, of the system. The demonstration was implemented, the proof of concept code was implemented in like a MBR infector. So it boots from MBR and it virtualizes the underlying operating system. So it really doesn't matter what this operating system is. It does not depend on any kernel, particular offsets in this operating system. It just virtualizes the OS from the very beginning. For example, if we run a Xen hypervisor with some guests, we can use, let's say, a shell on one of its guests, like we have a shell on VM2, and we somehow, the VM2 is not a privileged domain. Let's think that it is domain U. So It's user domain, which does not have enough privileges to override any original MBR. But if we have some backdoor, or if we found some vulnerability inside Xen or inside its management domain, DOM0, we can possibly ask this management domain to modify the MBR contents for us. And this is how we might install on the system. And on the next reboot, we will run a Bluepill, and the Bluepill will virtualize the Xen hypervisor. So Bluepill boot consists of 3 major parts. It's MBR infector, a Bluepill loader, and a main Bluepill code that supports nested virtualization, because it is mandatory to support this nested virtualization if you want to run some hypervisor like Xen or any desktop hypervisor if the user runs some desktop hypervisor inside his operating system, like virtual PC. This is the disk layout of the Bluepill boot infected disk drive. So it overrides the MBR, and it stores the original MBR on sector number 2, just right after the original MBR, and it fills the 20 next sectors with the main Bluepill code. Actually, this code is compiled by a C compiler, WDK compiler to be exact, and it is already a 64-bit portable executable file. So we had to implement some kind of a portable executable loader in Bluepill MBR just to enable long mode, and then use this loader to run the main Bluepill code. This is what happens when Bluepill boot is started. The Bluepill MBR gets this memory address at the beginning of this execution, and it's set to 7C00. It's always a constant. So then it assumes that the first megabyte of the physical memory is always allowed to be rewritten by any operating system loader. So it locates the main Bluepill's image at the address of 10,000 hex and copies the Bluepill boot code there. And it also enables long mode right in the MBR. So then it's Bluepill stage 1 receives execution, and it gets the map of the available memory using BIOS services in 15 and the function EA20. It gets the memory layout, finds some free space that it can occupy, copies itself there, relocates everything that it needs to be relocated, and then copies the original MBR stored on the sector 1 of the real hard disk to the memory at address 7C00, just to emulate the BIOS behavior. And then Bluepill begins to virtualize the original MBR in the real mode. This has been implemented for AMD systems because AMD SVM extension supports the virtualization of the real mode, while Intel VMX does not support virtualization of real mode. So we have to use some clever tricks to let the original MBR and original OS loader think that it still runs in real mode, while it possibly can run in virtual 8086 mode. And we have to emulate certain instructions, not very many actually instructions, like moving to CL0 and reading from CL0 and so on, just to overcome this behavior of VMX that it does not support real mode virtualization. But it exists only in theory right now. it has not been implemented in Bluepill. But if you take Xen as an example, Xen implements this V86 mode emulation quite well. And this happens when original MBR begins its execution. Let's think that original MBRs begin to execute Xen code at some point of time. So we have typical configuration of the Xenified system. Like we have some management domain, we have Xen. So Xen starts its management domain, then the management domain instructs Xen to begin begin to virtualize a few guests. So when Xen starts, it has to query the memory layout map. And since Bluepill does not virtualize any memory, it has to intercept this query of this memory map. And this memory map is obtained by calling interrupt 15 in BIOS. And it has to modify the map so that not Xen, not any other operating system loader will overwrite the contents of this Bluepill memory. Because if this overwrite happens, then it will most likely lead to a crash later on the next VM exit. So Bluepill informs Xen on each int15 call that a certain piece of memory is occupied by BIOS, and not Xen, not any other operating system loader allocates this memory later. So I will demonstrate a boot process of the Bluepill booted system. So this video was recorded on a live system, non-virtualized, of course. This is the beginning of this boot process, and you saw this. Let me show it again. You saw this blue frame around the screen that just for debugging purposes, it informs the user that Bluepill boot activates right now, and then you see the grub loader screen, and that means that the system has been virtualized already, so that we saw Bluepill boot initialization, and later we see this Xen booting process. It will run shell in a little while. So this system is not configured to run any hardware virtual machines, hardware HVM domains, but it's not that important because Xen enables virtualization flag right at the beginning of its boot process. So you see that everything works fine, and the system boots quite well. Yeah, and just to demonstrate that Bluepill boot does not depend on any operating system in particular, let's see the boot process of the very same machine, but with Vista operating system. So I just switched hard drives, and infected Vista loader with Bluepill boot. You see the blue frame. There is a boot options screen showed by Vista. So one might think, how does static root of trust measurement or the dynamic root of trust measurement can be used against this type of attacks? And this is why we use Xen Bluepill, because it's a good demonstration that static root of trust and dynamic root of trust do not really help in the scenario when we attack the hypervisor, the already running hypervisor. Because of course you can notice some difference in the boot process if you run Bluepill from MBR, but if you use some backdoor or vulnerability inside a running hypervisor, then this stuff, like starting root of trust or dynamic root of trust, will not help. So you see the situation when we have original MBR. For example, it is controlled by TPM module, so we are sure that the MBR is intact and all the boot process is good. But if we have some vulnerabilities in management domain and, for example, in Xen Hypervisor, then we can escape from one of the Xen Hypervisor guests to its management domain, and then from management domain obtain the privileges of the hypervisor. Or we can escape directly to the Xen hypervisor if we have some really interesting vulnerabilities inside. For example, if we have some hypercall handler in Xen, which is vulnerable to some buffer overflow, let's say, then we can install a Bluepill right from the VM2 domain, as shown in the picture. So again, static root of trust and dynamic root of trust does not protect from this type of attacks. We presented a talk at Black Hat this year. The talk was done by Rafał Wojciuk, and he implemented a special framework for Xen loadable modules, as he called it. So it was based on one interesting bug which was found in Xen by Rafał. This bug existed in the Flask module, and it allowed the DOM0 to escape to the hypervisor level. So there were many special hypercalls implemented with using this vulnerability. First of them was special hypercall for allocating some memory inside the context of the Xen hypervisor. And for example, one other hypercall was implemented to run arbitrary code inside this hypervisor. So we could use this framework to allocate a memory inside hypervisor context and run arbitrary code in it after overwriting its memory. And this is how we implemented a loader for Bluepill inside the DOM0. And to do that, we have to redesign a bit the memory management subsystem of the Xen Bluepill. So now it uses a single piece of memory for its code and data. It's actually pretty simple memory management. It just used in the beginning of the boot process of the Bluepill, in the beginning of initialization process. It just allocates a few memory blocks for VMCB structures or VMCS structures in case of Intel. And it's not used on any VM exit after. So I'll show you the demo of this attack. So this demo was recorded using a SSH connection to the vulnerable host. You see the shell, which we on a vulnerable host, and this is the DOM0. We run Xen detect just to be sure that Xen is active. The attack was targeted against Xen 3.2 system. We see that Xen runs one HVM domain, XP in this case, but currently the shell is in DOM0. So we execute the exploit code just to load this new version of XBP. And you see that actually it runs fine. So it's not really important how we use this bug, because the idea here is to illustrate that Xen Bluepill can be run at any moment on a running Xen hypervisor. We just have to be executed in the context of this hypervisor. So it doesn't really matter what bug we use to go to this level of privileges. So we run Bluepill, and after you see this line, your Xen has been Bluepilled, the system is moved to the nested virtualization state. So the original Xen hypervisor is not the primary hypervisor anymore, because Bluepill is the primary hypervisor right now. And we demonstrate that Bluepill is here by running a special bpnoc utility. This utility is very simple. It just executes CPU ID instruction with a certain magic value in one of the registers. And Bluepill intercepts CPU ID and returns another magic answer on a different register. So we can see that Bluepill is active. But you see that sometimes the magic answer is 0. So that means that not all the CPU cores have been subverted. We subvert only one core, but it's not really a problem, because we can use the same vulnerability to install Bluepill on a different core if we just happen to run on a different CPU. So we can execute this exploit a few times, and we just have to know the CPU number that we are currently executing on. And when we have this CPU number is differently than the original CPU number which we used to run the first Bluepill, then we are sure that we are running on a different core, so that we can subvert it also. So this is hardware virtual machine domain, HVM domain, which runs XP. So obviously it's not part virtualized. And you see that nested virtualization really works, because this HVM guest is not a guest of the Bluepill, it's a guest of its nested hypervisor, Xen in this case. And by the way, if you run this bpnoc utility inside this HVM guest, it still will return this magic answer, because there is no difference between two virtual machines. Like first virtual machine is the Xen hypervisor, and another virtual machine is its client, HVM guest XP in this case. So we can run CPU ID in XP, and it will return this magic value too. So we can control the behavior of every guest which runs in the system, not only the nested hypervisor, but all its guests too. If we have Xen 3.3, then we need to use some exploit to bypass its protection, its memory protection, which was introduced in 3.3. I mean the VTD extension. As we demonstrated, the Q35 chipset exploit on Black Hat, it worked quite well, but it's a different topic for discussion. So how could we detect a Bluepilled Xen? So obviously we cannot use a detection for any VMM running, because of course we have virtual machine manager running, and it is Xen manager. But the question is, how can we detect that this Xen hypervisor is not a primary hypervisor anymore, and we have some malicious hypervisor above it? So one idea is to use a timing analysis to see the time that takes certain VM exits to execute. Because, of course, if you have a stack of hypervisors, then it will take much more time to service any VM exit, because the information about this VM exit should pass through all the hypervisors that are involved. Let's start with impact on paravirtualized domains. For example, domain 0 in case of Fedora 8, for example. So the impact is 0 because there are no actual VM exits on paravirtual domains by the definition, because every virtual domains, any paravirtual domains, any paravirtual domain will generate a general protection fault if the CPU encounters instruction like vmrun, for example, because vmrun instruction is a privileged instruction, and paravirtual domain kernel does not run on the most privileged level, so it will generate a general protection fault, not a VM exit. So adding another hypervisor will not introduce any performance impact in this case, but on AMD, of course, because on Intel we have obligatory intercepts like CPU ID, INVD, and move to and from CR3 register. So this instruction, like CPU ID instruction, is not privileged, so we can run it in paravirtual domain, and still it will generate some. It will introduce some performance impact because we have a stack of hypervisors enabled. So what about hardware virtual machine domains? This is a picture that illustrates the impact on HVM domains if we use full nested virtualization and some other variations of this algorithm of nested virtualization. Let's say these are just some optimizations that we tried to implement just to see how far can we go to minimize the performance impact. For example, as I said earlier, we need to use CLGI, STGI, and vmload, vmsave intersection just to be sure that no problem will happen when a nested hypervisor will get the information from its guest state and so on. And it turned out that in case of Xen, we can safely discard these interceptions. So we don't take any, we do not service any of these interceptions, and still Xen hypervisor works well. This is good because it allows us to minimize the performance impact to as low as 2,000 CPU cycles, because original Xen takes, for example, 5,000 of cycles to service typical VM exit, like CPU ID, let's say, and Bluepilling the Xen takes 7,000 cycles. So 2,000 cycles is added by the Bluepill. So this is how far we are from the holy grail of the invisible malware. Of course, you can observe this impact on hardware virtualized machine domain. You see zero performance impact on AMD paravirtualized domains. So this is very cool too. So a few words about another way of detection and prevention of the blue pill. So not exactly prevention, detection. HyperGuard is a project run by Phoenix Technologies. It is supposed to run in SMM mode, system management mode, and it is supposed to check certain regions of physical memory from time to time to find the modifications, to find out what had this memory been modified or not. For example, if we consider these Xen rootkits from Rafał Wojciuk, which modify the hypercode table, we cannot really protect from this type of detection because system management mode is more privileged than typical ring 0 protected mode or long mode, and there is really no way to hide from this analysis run from system management mode. And this applies to Bluepill as well. So if we have some specific signatures for Bluepill code, we can find this code from the SMM module. It is possible also to analyze the CPU state from a SMM module, but it's a bit tricky to do. So this project is still in development stage, and we hope that it will help somehow to protect against virtualized rootkits and virtualized malware. Okay, so these slides are available at this address. Do you have any questions? No questions? Thank you very much.